Jonathan Clarke. He is the president of the Mars Society of Australia, and he's going to be talking to us about Regolith resource requirements for an expanding Mars facility.
Okay, well, good afternoon. I'll try and run through this briskly. And the question that faces us is, when we're talking about mining on Mars, what scope of mining are we talking about to support human operations? Are we talking about large-scale mining, or are we talking about something that's more, perhaps what we would call subsistence mining? The second question is, as the scale of operations increases over time, how and at what rate will that increase occur? The third question will be, what sort of equipment are we talking about to support these operations? What scale of equipment? And because what we are about in Mars Society is very much testing things on Earth in analog environments, is how can we test some of this equipment on Earth? So in terms of stages, I use 3 examples to illustrate the stages of the expanding Mars facility. The initial mission, when people first land on Mars, which might be represented by the Flashline Mars Arctic Desert Research Station on Devon Island, that we've heard a bit about. I spent a month there back in June, July. A larger facility after several missions, facilities expanding, the Mars Desert Research Station in Utah. And then, conceptually, some of the grandiose visions by Elon Musk and others could be represented by McMurdo Sound in the Antarctic, or in this case, the little town of Regolith, again, up in the Arctic. But regardless of the scale of operations, there will be common features illustrated by this rather nice piece of artwork. There will be some form of ISRU plant processing local resources into useful commodities. We'll need some sort of machine that will be excavating, and there will be a range of applications illustrated by a berm, in this case a rather inadequate protection against your rocket exploding on takeoff or landing, a resistant pad, and of course various undescribed materials going into various storage facilities. I've tried to scale the amount of material needed to support these 3 types or levels of operations. So the initial study, the initial mission, the Mars Society of Australia's Mars Oz mission, for 4 crew, a semi-direct mission architecture, would need about 1.6 tons of hydrogen to send the ascent vehicle back into Mars orbit for the journey to rendezvous with the transfer vehicle for returning the journey home. 1.6 tons of hydrogen is about 14 tons of water. Assuming 10% water content in the regolith, that becomes about 144 tons of regolith. Mined over a 2-year period, that comes down to 200 kilograms of regolith a day. And if you look at the sort of bucket that you put on the front of a little utility vehicle like a Polaris Ranger, that comes down to about 1 of these buckets every day to feed your plant that produces your propellant for the return home. The Mars Direct version 2, which is rather larger than the more popular, more widely known version 1, would require 8.6 tons of hydrogen, which is 78 tons of water. Scaling up, that comes down to 1.1 tons of regolith with 10% water mined per day, 5 of these or 1 of these. If you look around the place, you'll see a Bobcat S560 doing various tasks. And again, SpaceX's grandiose plans, which would need 63 tons of hydrogen to make the methane fuel. That converts to 563 tons of water, 5,600 tons of regolith, which sounds a lot, but still comes down to just under 8 tons of regolith mined per day or per sol. 34 of these buckets, or just 8 of these ones. So we're not talking about the super pit here. We're talking about small-scale operations. Other requirements. When you first land on Mars and you set up your station, even on a station, you'll be needing to move things around. So here's the generator shack for FMARS, and people by hand have cleared a track so you don't trip and break your neck when you go to start the generator. Astronauts on Mars might do it by hand as well, or they might use a small blade attachment on their utility vehicle. Larger scale, and we've heard about this already, you might want to start burying cable work so as not to cause safety hazards and also reduce environmental wear and tear. So here we have a small excavator being a trench at NBRS to connect the new solar panels to the infrastructure. Large scale operations, this is up at Resolute. The weather station there is built on a large platform of fill, which is essentially just gravel from the beaches, shoveled up by a front-end loader and put in a truck and dumped there. And that's important not only to keep the ground level, but also because this is a permafrost environment. There is ice about less than half a metre below the surface of this environment, and if you have buildings generating heat, you potentially can melt the permafrost, which causes subsidence and other problems. And again, on Mars, where there is permafrost everywhere, some of which we know contains ice, again, we may need to consider building platforms or other mitigation means to preserve the permafrost from heat radiated by the buildings. And then, of course, we'll need to prepare foundations for more permanent structures, or things like observatories in this case, where you've got to make sure that things don't move with day and night cycles, Mars quakes, or other movements. And the demand for that regolith is going to increase exponentially with the size of the settlement. So here's Resolute Bay from the air, the town of Resolute, and you can see that surrounding it, there's all of these areas where people over the years have quarried the old beach deposits and the river delta deposits to supply fill, to supply road base for the various gravel roads. You see how the roads built up off the ground. And for a small station, initial station on Mars, the requirements for regolith material is going to be minimal, but by the time you get up to something this size, it becomes very, very substantial. Some other regolith movement requirements. Here we go, cut and fill, something built into the side of the slope. You've got to cut into the landscape and build out a platform. Trenching and pipe lay, rather larger than the ones at NBRS here. This was a new water supply going into the town. Various platforms being constructed. Here's another way of dealing with permafrost. You actually elevate your building above the ground. And building of causeways for the road back to the weather station again. And for your expanded Mars facilities, again, some Mars artwork can be very misleading, but some can be quite good. Here's a very old one from Carter Emmett from 1986. And varying of infrastructure from radiation protection, site leveling for these modules, for the greenhouses, ISRU plant, mysteriously processing the atmosphere, and preparing the tracks for movement around. And various people have referred to the importance of this because, having worked on many mine sites, I have to agree that you do need to minimise dust from both a safety point of view and preserving the vehicle maintenance. So what sort of equipment would you need and what sort of operations? I've divided them into excavation, trenching, levelling, transport, auguring and drilling, and rock breaking. And all of these things can be supplied by a relatively small range of machines, attachments to vehicles, and at a fairly small scale. So here's a Polaris Ranger. Again, you can fit this with a tip tray, you can fit it with an excavator bucket, you can fit it with a bulldozer blade that can either push stuff around or grade material, and you can have a variety of augers on the back. You want to move things up a scale, you're looking at something more like a bobcat, and that will, I suspect, handle most of your earth-moving requirements for up to the size of a small station. And for a transport chassis, a light truck, 5-6 ton capacity will be enough for most purposes, I suspect. because you want to minimize the number of range of vehicles you want to move around. You want to take to Mars, you want to keep it perhaps down to 2 or 3 basic chassis at the most. Okay, now the other thing to remember, this is the point I made earlier, is that, again, grandiose artwork. I think someone was confusing Mars with Arrakis. You're not going to be initially talking about this sort of scale plant crawling across the surface. We're not mining spice. You're talking about very, very small scale operations. Mum and dad operations. And this is quite literally a mum and dad operation, not mine. But in the far southwest of Tasmania, for many years, they were mining tin. Half a kilogram of tin per tonne in alluvial gravels, underneath 1.5 metres of overburden. Gravels about half a metre thick. 5 tonnes of cassiterite produced every year, operating 5 tonnes per hour, 36 hours per week. Husband-wife team, and over a year they're mining about 10,000 tonnes of gravel and 22,000 tonnes of overburden, affecting about 100 by 100 square metre area each year. And that gravel is then recycled for use to build trackways, foundations for buildings, and so on. They also, out of interest, processed the tin on site into ingots and shipped it to Hobart in their Huron yacht, which was their licensed cargo vessel. And the thing on Mars is, even for large-scale mining on Mars to support a large-scale Mars settlement, we're not going to be talking about 22, 30-odd thousand tonnes of mining per year for a long time. So we're really going to be talking about very, very small-scale mining. And so Regolith on Mars will be smaller than even the smallest sort of mum and dad operations, mining operations that we see on Earth. So to meet the requirements, here's some vehicles, analog vehicles. The John Deere Gator, the Polaris Ranger there. The Toolcat, very nice little vehicles. The size of the 228 kilograms in the bucket. The Toolcat can take over 600 kilos in the bucket. The Dingo, very nice little vehicle. You just sit on it and you drive it around. And that can take about 340 kilos in the bucket. And of course the S590 Bobcat. So the research possibilities are this. The small-scale mining of Mars to support initial missions, and indeed initial settlements, a few tonnes per day maximum, allows us to do testing at full scale. I've seen some lovely work being done at this shown at this conference and previous ones of people using small-scale models, robotic models, doing things, and that's great. But we don't need to do it at a small scale. We can do it at full scale and still use very small machines. And the sort of machines that you can buy off the shelf. And the Dingo, this is a motorised wheelbarrow, this is a little loader, and they can be operated remotely. So these are teleoperatable machines. And you can then potentially look at automating those and working in a full-scale mining operation on Mars, or the equivalent thereof. And because it's robust equipment, you don't have to nursemaid it because it's already field qualified. And you can test a wide range of potentially difficult environments, mining clays, mining gravels, mining gypsum, whatever it is you want to test on. And there is certainly a lot of potential for student team projects using these existing machines, I suggest, and corporate sponsorship. In the past, we've had some very good discussions with Dingo over collaborating with them for looking at small-scale mining experiments. So conclusions. Initial regolith mining is going to be small-scale, or likely to be small-scale. Site works, water extraction, with the water extraction dominating. Later on, site works are going to dominate because they're going to increase far more rapidly in terms of requirement than your water extraction. But even then, the water handling rates, or the regolith handling rates, are going to be low. And we can test those at full scale on Earth with off-the-shelf technology before refining it to specialised equipment that we want to use on Mars. Questions?
Yes.
So thank you. I think the basic observation that this is small scale is really important, that we have to communicate that to our management, because the perception is that mining is right away, you think of big yellow machines. So that's an important perception that we have to address as a community. However, I would caution on using commercial off-the-shelf equipment designed for Earth because of the gravity and the reaction forces. So the traction is proportional to the coefficient of friction of normal force, which is dependent on gravity. So what we found is when the Apollo astronauts drove on the moon, they said it was like driving on ice. And they're skidding around all the time. They can't go very quick because it's just lack of control. So I think we have to reimagine the equipment a little bit more than what you're suggesting. The basic premise is good, is that the equipment is small, but I think you're going to need different solutions because of the lack of reaction force. When we have a robotic mining competition at Kennedy Space Center where we have over 50 universities come every year with robots that weigh 80 kilograms or less, and we do have front-end loader machines like that showing up, they never do well. So I'm going to caution, I think I would like to caution you on that statement that you could just take Cox equipment and go use it.
I agree. This is the problem of scale, and I think there's certainly a minimum size below which it's just not going to work. What do you think of the possibility that we use, we take a lightweight machine to Mars, and then we use ballast? We fill up panniers and boxes with.
That's a great solution.
Yeah.
That's ISOU, right?
Yeah, that's right. Yeah.
That is the way out of it.
Yeah.
Do we have one more quick question for John? Yes.
In your calculations there of the tonnage needed to be moved around, do you include any kind of processing efficiency for the water or losses, and also about clearing out waste and moving it around too, so that adds?
Yeah.
It's the same material being moved twice.
Very much, and that will depend on whether you have an integrated all-in-one machine that dirt goes in one end and water comes out the other, or whether you dig and carry it to an immobile plant. I use 10% because that seems to be an approximate mean. I mean, you might be mining pure ice or pure sulfate, and the value will be lower, or you could be mining just the standard surface regolith, which is probably only about 3 or 5%. So this is very much back to the envelope calculations. But even if you sort of double or triple increase by an order of magnitude, the sort of tonnages that you're moving every day are going to be quite small compared to even a small terrestrial mining operation.
Okay, can we thank John again for his talk? So next we have